Over to you, sir.
Yes, sir. Good evening, everyone. Thank you for the introduction. So thank you for the opportunity given. So I teach this module to your third years. Today I hope I will be able to make most of you interested in this exciting field. Now, the thing about this field is whether you like it or not, many of you will start using this in your final year projects and other projects. So therefore, it is very good to get an early start on this exciting field. This is the field of highest demand in the world right now. So therefore, that is also one more reason to learn about this. Learning does not mean that you just memorize things, but you should be able to do these things. So we will go through this and I will show you how to get started. Maybe this 2-hour session is not sufficient for you to get started. So several hours of teaching or self-learning is required. So for that also, I'll give you some pointers in this. So in this talk, I will talk about why computer vision is required now. So what happened a long time ago and why is this needed now, or why is it there now? Why did it receive a lot of attention now? And then briefly talk about conventional techniques, and then the perceptron and convolutions, and then convolutional neural networks, and then some image classification methods, then object detection methods, and some a little bit of future trends. Okay, so let's get started. So just to start, let's look at some videos maybe, and then we'll be able to make ourselves more interested in this. Okay, so let's look at the first video. This one is from the CVPR 2022. Maybe before showing the videos, I should introduce what these things are. See, in this world, the most advanced things that people discover are presented in conferences and journals. So journals are printed ones. They have maybe 12 issues per year. So you can submit at any time. But the conferences have a date, so they have paper acceptance and so on. So CVPR is a topmost conference, not only in computer vision, but it is a top conference of all conferences in the world. So there, now you can see why we say that it is so important. So I can show you that with the Google metrics. So if you go to Google metrics, you can see the topmost journal. It's a journal. It's called Nature. So it has 414 H5 index, and then New England Journal Medicine, and then Science, and then of course the CVPR conference. So you can see there are this is also a medical conference, Advanced Materials, Nature Community. Then you have the ICLR also, International Conference of Learning Representations. That's also a very important conference. Neural Information Processing Systems, as famously known as NeurIPS conference. That's also important. So you can see the advancements, the computer, like this once again, the International Conference of Machine Learning, European Conference of Computer Vision, International Conference of Computer Vision, and then you have the journal somewhere, AI conference. That's also an important machine learning conference. IEEE transactions on pattern analysis and machine intelligence. So you can see they are within the top 100. So I will show you, if I may, our publication record also. You can see, if you take these are the great works done by our students. And so I have publications in WACV. So if you look at now, you have to go to the subcategory to see the computer vision only conferences. For example, if you go to engineering and computer science, then go to the subcategory of computer vision and pattern recognition. Pattern recognition means machine learning. So there you can see, of course, CVPR must be at the top, and you can see the WACV is right here. In application computer vision, ICIP, International Conference of Image Processing. So I have a WACV paper. This is the recent CVPR paper that we got accepted by, written by our firm. So for 2022, it will happen in June. Then this is a WACV conference. Maybe you have heard of his name. He's the gold medalist. This paper, one of the authors is Amaya Dharmasiri. the famous island-based in Universe, maybe you heard her name. This one is by Osha the Jayasinghe, the famous, very famous island-based Osha the Jayasinghe. Aditya Dias, this is also island-based. And this is not a computation paper. This one is also ICPR, that's a machine learning paper. Then there was an ICIP paper also somewhere. This is also WACV paper. This is Jatushan Rajasekaran CVPR paper. And there's an ICIP paper also. This is an International Conference Image Processing. Yeah, so you can see we have the credentials to talk about this at least. So that's the frontier. That's the very threshold of science in the world, science in machine learning. And yeah, of course, computer vision. So therefore, I will interest you on this. So CVPR 2022 is the latest conference. So this is not our paper. This is a MIPNERF paper. I saw that in Twitter. I think it's very nice. So we will see that. So in this one, I hope I will do justice because I did not read this paper to this person. So what they do is they will look at different angles of the scene and are able to make a 3D because you can see the depth map, right? Like things that are close to the camera are in blue, things that are far away from the camera are in red. So unbelievable, right? Unbelievably nice. So these are called the NERF kind of papers, neural radial fields papers. Yeah, NERF was the original paper, and then this one is a new paper published this time. Yeah. So you can see the CVPR 2022 message. So I hope you get interested about this thing. So then this one is the giraffe paper. It's a CVPR 2021 best paper award. There you can see they are once again. That's also this construction.
Hi, my name is Leon. I'm from Bauru, São Paulo, Brazil. After graduating in 2014, I was working.
Hi, I'm Michael, and in the following I'll present Giraffe, representing scenes as compositional generative neural feature fields.
These are image
generative models are great.
Or generative models.
In the typical setup,
not listen to the theory,
idea
but
of this
look at what they have been able to do, the results.
Factors of variation.
They can generate.
We achieve this by incorporating a compositional 3D scene or adding more objects at test time. And here we show results for changing the depth of the object.
You can see now it is not far that we manipulate these objects and
here we do the same for the object's appearance.
So these are face generations, face manipulations, all these things. So these things are not far away from us anymore. Because one thing in the computer vision community is you have to make the code available. So unless you are a very powerful person, you have to make the code available. So we also have made our code available. So this is an ICLR work. So because of the code availability, a lot of people can replicate it. This is an old paper, but I like the pictures in this. So this is called progressive growing GAN. They looked at so many celebrity images like so. And then using those images, they were able to synthetically generate celebrity-like images. Those images that they generate, they are not there in the world. I mean, they are not human beings. They have been just synthetically generated celebrity-like images. Absolutely beautiful one. So this is the so-called training set. And then now they will show you the generated images using the Celeba HQ image. So this is generated image, stunning, right? Stunning images. No one is there in the world like these people. Yeah. I think the first one is the most beautiful. Yeah, some have some artifacts are also there. Yeah. See. Oh, yeah. Okay. That's good. So these are the things that people are doing right now. So if you also seriously study this and reach these conferences, you can also be a part of that very exciting scientific world. Okay, yeah. So just to entice you even more, for example, if we talk about this person who got the first CVPR paper, I think the first one for our country, he got offers from both Stanford University and Carnegie Mellon University to do his PhD, and he was given tickets to fly over there and see those places. He couldn't go, so but now he's at UC, not Carnegie Mellon, Berkeley. He's at UC Berkeley. Beautiful career, and I think his first salary was like that of a CEO, right? He went to Dubai for his first job. Of course, research position at a university. So since then, a lot of our students have been going there, so to different places. So because of this great work that they do. Yeah. So you think that Sri Lanka is a small country who notices our work? The way to get noticed about our work is to be there at these great conferences. In these conferences, it does not matter what your country is, what your skin color is, what your name is, it does not matter. Your work matters. Only your work matters. So this opens up the door for our country, Sri Lankans, and all of us to be there. So we have one CPR paper this year. India has 400 papers. India has 400 papers. So you can see the situation, right? So that's why people like you, intelligent and enthusiastic people like you, should get together. Tag along with us, tag along with my group of my students, and work on these problems. Work on these problems and try to get a publication. Maybe not at CVPR. CVPR is hard. It is hard even for professors. It is hard. So maybe some other publications, and slowly move there. Okay. So yeah, that's the target. So, but how to get there is the thing. So I will show you few things about how to do computer vision and so on. But there's a lot of work to be done. So these are the top conferences, as I mentioned. So these are the machine learning conference. These are the computer vision conferences. CPR is the top, and these are machine learning conferences, and these are the journals, computer vision and pattern recognition journals. So yeah. Then if you ask how to learn, so my students like Rehan, who are in third year, know that we use Python for that. So, I mean, I used to use C++, but now you don't need C++ anymore. You can work with Python. So then you have to work with Opencv to do computer vision. And then later on, you will have to work with a deep learning framework like TensorFlow or PyTorch. TensorFlow is by Google, PyTorch is by Facebook. Or PyTorch, right? Yeah, so I'll show you a very brief example of Opencv, a very brief example of TensorFlow tonight. And then you can take a course. Now you can take a course listed in this book's website, for example. There may be good Coursera courses, but I have not investigated those. So if you ask me what are the good books, like for image processing, Gonzalez and Woods is a great book. Forsyth and Pons is a great book for computer vision and image processing. Richard Serisky, this book is free. There is a 2022 edition. So you can download that as a famous researcher. And then at least browse through the pages, like what do these computer vision people, I mean, if this is topmost science right now in the world, what do these people do? Things like that. And Milan Sonka book, that's also good. These are the books that I know of. There can be other books, but these I know are good. Good books. Okay. Yeah, that's the general things about what's happening in the field and how to get into the field. Okay, so let's look at what is deep learning that is there in our computer vision. So computer vision adapted deep learning starting from 2012. So deep learning is a machine learning and advancement that allows the systems to automatically discover, learn representations. It's called representation learning using a stack of multiple deep layers of neurons, and which is called a neural network. So you learn how to represent things also. So I'll show you what the difference between the conventional learning and now. But before that, I will answer why now. What's the reason for now? I mean, why did it happen before? So you see, like people had great processors like Intel processors and so on for computers. So maybe you also have Intel processors or AMD processors on your computers. But these processors are not entirely parallel, right? They have multiple cores and hyperthreading, but not entirely parallel. So what are entirely parallel are those GPUs. Like, for example, if you take RTX 3090, great NVIDIA gaming card, and the massive massively parallel. So you can run these deep learning networks in these ones. You can train them. And this is the most expensive card, NVIDIA 800. We don't have those. we have cards that are sort of in between, close to this maybe with us. So now these cards came into being. Then people were able to do things that were never possible to be computed because of these cards. And then on the other hand, people were able to process these things on the cloud. So today the examples that I show would also be on the cloud, Google, using the Google Colab or the Collaboratory. And then frameworks like TensorFlow and PyTorch came into being. These are excellent and extremely optimized frameworks. They are beautiful. So in using those, you can code them quite quickly, and you can train them and you can test them. And then to deploy them, you have languages like ONNX, representations like ONNX and TensorRT. So using which you can put that on a device so that you can, this optimized one, you can run faster. So that's why it is. Okay, now research community had these things with them, but now the industry has realized that they also need this. For example, face recognition, who this person is. Yeah, you know that the computers and your phones log you in by looking at your face, and they are extremely accurate. So these are advancements of computer vision. So people realized that you can do things with these computer vision, even the fingerprint scanners that are there on your computers. Yeah, and the computational power came to be available. Yes, that's the reason why deep learning based computer vision suddenly became extremely popular. So just to actually the introduction also, the person nicely said this. So what are these things? Like you have this umbrella of artificial intelligence. I think this was coined by Peter Novick, artificial intelligence, and within that there is machine learning. And then within machine learning, you have neural networks, and within that you have the so-called deep neural networks, many layers of neurons, so multiple deep layers. So when you say deep learning, you don't think like, I mean, you know, this is a man who learns deeply, not like that. So people were angry about with me also. So for some time for saying deep learning, I mean, deep means you have many layers, like more than 8 layers. That's sort of deep learning. Yeah. So that's where it is like deep learning based. So if you take computer vision, I would draw the computer vision circle now like this. Yeah, this is the computer vision circle. So there are things that are in deep learning other than computer vision. I will show you those fields a little bit later, like natural language processing and so on. They also have strong requirements of deep learning. Yeah. Okay. So now let's look at the difference between the classical computer vision and the deep learning based computer vision. Now let's take first of all the image classification example. Now, for example, let's say we have cats and dogs, cats images and dog images. So we present this image to our processing system, and there you have something called a feature extractor. So what that would do is take the cat image and represent that using some kind of a signature. So you can think about this as a signature. So we call it a feature vector signature. And then there's a classifier. Classifier would say cat or dog. Classifier would say cat or dog. So labels are here only 2 labels, cat or dog, right? Then if it this makes a mistake when you present a cat, if it says a dog, that means a mistake. So there is a loss occurring. So what you do is you use that idea about the loss to modify the classifier. Okay, classifier, you did a bad thing, and the classifier will have to change itself. And for that, we use a so-called backpropagation. Yes. This is the classical approach of computer vision. But when the new approach came, the neural networks, you can see there these two combined together. So the feature extractor is hand-coded in the previous era. Now the feature extractor is also trained by the losses that you need. It is also trained. So that's the advancement in this neural network-based computer vision or deep learning-based computer vision. Okay. Now I'll show you now. Some people say that you don't know what's going inside these networks, but I think we know now what's going inside these networks. So actually, if you take a simple network which does not have many layers, but only 2 layers, maybe 2 layers, maybe one. So when you get these signatures, when you get these so-called signatures, they will turn out to look like the images that they would recognize. The signature for the plane will look like a plane. Signature for the car will look like a car. Signature for the bird will look like a bird. When you train and train and train, they will turn out to be like that. So you can see it is looking for similar things that are in the image by getting this template or the filter or the learn thing or the signature to look like the image that you want to classify. So if you present a cat image, the cat filter will give a high score, but the deer filter will give a low score, something like that. So the very first neural network that became famous was the so-called AlexNet in 2012. And they had these 11 by 11 weights, and when they looked at it, people saw that, okay, there are these edges, things like edges. You also look for edges, right? If I ask you to draw a table, you will do this, like you will draw the edges, right, of the table. This is what you will do. You draw the edges. So like that, this neural network also has looked at the edges, yeah, and some color-based, color-based dots, these things like that, alternating colors, things like that. So that's what it has looked for. Okay. So this is a general picture of what is deep learning and why it happened now, and the difference between the conventional computer vision and current deep learning based computer vision, and where this deep learning stands in the general area of artificial intelligence. I hope that is clear to you. You can interrupt me and ask a question at any time. So may I know whether I am well heard? Ihan, am I well heard? And you can see the screen properly, right?
Yes, we can hear you.
Yeah, okay, excellent. Yeah, thank you. All right, let's move to the next one. So let's briefly look at this learning problem of so-called image classification. So assume that you have so-called training examples. So you have how many apples? 1, 2, 3, 4, 5, 6, 7, 8 images of apples, and 8 images of pears, 8 images of tomatoes, 8 images of cows, 8 images of dogs, and 8 images of horses. So these are called training images. So we have been given the training image and their categories. We know that these are apples and so on. So then what we do is, okay, how many possible representations are there? If you take an n by n image, this is, let's call this an n by n image. For me, it looks like maybe 100 pixels by 100 pixel image, 100 by 100 image, let's say. So that is n by n. So n by n vector of length n square for color images 3 times n square. That's the image that we give to the system. And then what the system has to say is like take them in and do some function and train that function. And if you give something like an apple to that function, it must say, okay, it is an apple. This is what training means. Okay. So the simplest training thing that I showed you even before is this single so-called a linear classifier. So what you do is now assume that you take an input image like a cat, and we represent that cat using a 4-number signature. Actually, to represent the cat, you will need many more numbers. Okay. So for this example, I'm taking as an example a 4-number signature for the cat. So discovering what this signature is the task of this learning problem. And then these are my learned weights. These are my learned weights. For example, in reality, the learned weights for the cat are like that. I mean, there are a huge number of numbers here. Maybe I do not know. This is like I don't know the exact size. I think 32 times 32. I think 32 times 32 maybe pixels. So that's a humongous amount of numbers, right? So that's what it is. But I have shown it using 4 numbers. So these are the 4 numbers that actually the cat is represented. This is the signature. So these are the templates learned while we train the network. So what we would do is we take this and multiply this, take this and multiply this, take this and multiply this, take this and multiply, and then add this number also called a bias, and then we get the cat score, and then we get the dog score, and we get the sheep score, and the highest one we pick. It's a dog, but actually this is not correct, right? It's a cat, right? Weird looking cat. Why? Because we have not finished training this. Once you finish training, these signatures will start looking like cats. So these are the ones I have represented. Okay, if you take the horse, you can see a head here and a head there. What's the reason? Because in the training image set, there have been horses looking this way and that way. So it learned both these things. Yeah, I hope this diagram is clear. So these are for CIFAR 10. So if you are in a computer vision first course, we will teach how to do these things. And if you do things fast, we teach how to do these things. Otherwise, there's no time to teach all these things. Okay, so this paradigm I explained. So if you take the CIFAR 10 label, so it's not like cat, dog, airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. These called these are famous data set called as CIFAR 10, I think. Yeah, CIFAR 10 data set. So there are data sets to train them, and then there is a very large data set called ImageNet and so on. So okay, so now how does this thing work? So in a slightly mathematical manner, you have the input image. So this is equal to the number of pixels that are in number of dots in the image, and you have the weights. Those weights are the ones that I showed as images here. These are these W's. And then you have some kind of a thing that adds these things, you sum them, and you apply some kind of threshold like that. So sign. So Wx plus B, W times X plus there's something called bias. And this is called the perceptron. This very famous discovery that was made some time ago. So you get the sign of that thing, assuming there are K classes, you will have this W K times D. We will not worry about that. So these are early things that people said about these neural networks. So you can see in 1958, New York Times, this America's famous newspaper, said it's about this Navy device. They have discovered neural. Maybe you can read this for yourself. So you can see what they predicted that did not come true during those days with 100,000 US dollars, but now it has become true, right? After that many years. Okay, then people said, okay, just one layer is not enough, but we will have many layers. So then people said, okay, rather than these many layers, these all are connected together. Let's not connect all, but only connect a few with one. Only connect another few with one. So this is called convolution. So for signals and systems, maybe you learn this. So I'll show you what this convolution is. For example, now if you have a box filter like this 109, 109, 109, 109, 109, 109, all 109s, you keep it here and you see at the center what you get. You multiply what is underneath. So when you multiply, you can see all zeros multiplied by 109s, you get 0 here. And you move it here. Now there's 190, right? 90 times 109 is 10. You put 10 there. At the center, you put 10. You move to the next place. And here you have two 90s. So 90 times 109 plus 90 times 109, you have 20. Here you get 30. Here you get 30. And so on like that. So here can you see how much you get? 10 plus 10 plus 10 plus 10 plus 10. You get 50 there, right? Like that. So you get like that. So this is the output of a convolution. Yeah. So this is just one convolution, but that's not enough. So these are these non-convolutional networks or dense networks, or we call them sometimes linear layers. And then these are called fully connected layers, dense layers, or linear layers. So they take to compute one node here. You can see arrows are going from all these nodes. Arrows are going from all these nodes. So that's why this represents that arrows are going from all of them. So this is an image. Now to compute the second one, arrows are drawn from all places. But if you take a convolutional neural network, you look at only a neighborhood. Maybe this is a 5 by 5, 3 times 5 by 5 neighborhood. So 3 means the depth of the image, RGB colors, and then you learn these weights. So this is one feature map. And if you have one more convolution kernel, you have another feature map like that. And then there is another convolution layer. You take all these things and multiply and add. So that's how convolutional neural networks work. So for example, let's take the CIFAR 10, like 32 by 33 images of color RGB. That's why there are 3. So this is the size of that data chunk. And then we run a convolution kernel over there and we get the output here. And then one more convolution kernel, and there's a bias also. We get the output here. Like that, from one image, you generate that many outputs. Yeah. So this is the operation of a convolution layer. So, but when you have more than one image, a batch of 4 images like that, so we will have 4 of them. So we feed them in batches, like 4 images at a time, actually like 64 images at a time and so on. So this is the output that you would get. So I will not go about these numbers. So if you do the course, we can talk about these numbers and so on. So let's look at this operation pictorially. Now let's take that this is the convolution kernel. So maybe you saw that in regard to the AlexNet that we discussed, you run it through. So when you run it through, the similarity to that kernel will appear like that. You know, that's called a feature map. That's one of those layers that we saw. And then you take another kernel and run it, and you get another feature map. And like that. So these are called convolutions. And those those little boxes or kernels we learn. So then we apply a so-called non-linearity. So that's there are many non-linearities, but people usually use a so-called ReLU non-linearity. What that means is if the number is less than 0, you put 0. If the number is greater than 0, you put that number. That's the one. So there are the non-linearities like sigmoid, hyperbolic, tangential, leaky ReLU, and so on. Okay, then you have something called spatial cooling. That means you take a 2 by 2 rectangle and take only one value. That's called spatial cooling. And then these convolution neural networks have the image, convolution and pool, 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 and you have a couple of dense layers. So this is the early convolution neural networks that people had for classifying images. So this is the earliest one, the so-called AlexNet in 2012. And when they published this in 2012, the whole world was surprised by the amount of great results that they obtained. So, yeah. So now let's briefly look at the CNN architectures or convolutional neural network architectures that are available for classification. So classification means giving a label to an image, cat or dog, something like that. So very first ones was so-called LeNet. So this was an early one by Jan LeCun. So actually my students have a picture with Professor Joshua Bengio. So he had this MNIST data set, and he was able to recognize the digits like using convolution. He called it subsampling, but that's pooling we know now. Convolution, subsampling, some fully connected layers. He was able to get that working. Actually, I can show. We can code it in maybe half an hour. This whole thing and get it running in a couple of minutes. Now that we know about these things. So then AlexNet is a slide. It has 8 layers. So it's a simplified way of showing the so-called AlexNet. Then they came up with VGGNet. So this is the AlexNet had 8 layers. So VGNet had 2 versions like 16 and 19. That many layers. And then they had a thing called GoogleNet by Google. So they had that many layers. So they had some advancements also, which I will not describe. And then there came the residual network, this very famous contribution called ResNet. And then, yeah, excuse me. Sorry about that, started sneezing for some reason. So then you had this so-called residual connection in the ResNet residual network. So I know that you do not understand, but at least you will remember that there is this residual connection in ResNets. So then people thought about, okay, does the network have to be bigger and bigger? Because if you take the ResNet, they had like after VGG9, 34 layers, 50 layers, 101 layers. So a lot of computation. So when you compare these people, operations, giga operations. So 25 giga operations, 40 giga operations, and so on. And then the top one, accuracy. So then how accurate is the class image classification? So we can see the ResNets are over here, and then this inception one is over there. So this is like 2017 data. Now things have changed. So I will not go through all these details, but you are most welcome to look at the slides. And I took this from this place, papers with code, image classification on ImageNet. Now what the situation is. So you can see top one accuracy has reached 90.94. So here we are just showing the top one accuracy 80% in 2017. Now you can see. So these use so-called vision transformers. So it uses transform and trained on this extremely huge data set called JFT3B, I think. So it's a 2022 work and so on. But this code is not available. But here the code has been given. It's 90.88. That's also great. So that many number of parameters, right? It's difficult for us to handle. I mean, these are done by the large companies, I think. Yeah. So if you go to this place, the papers with code, you'll be able to see that. So maybe I will do that so that you can have a look at it. So they have the leaderboard. You can see in the leaderboard, you can see which one has the highest accuracy. So this VITG has the highest accuracy. So this one, this has code. So it's huge number of parameters. So maybe you cannot train them. Training transformers is hard actually. But there are some ones which have this number of parameters. So the efficient net, I think we can manage. Yes. So this is about image classification. That means giving a label to an image. So these ones I will not discuss. But if anyone is interested, what about this, I can discuss later. So in this, we learned some concepts like data normalization is required. What that means is you have to normalize data between some two numbers. So you cannot have like large numbers like 200. So initializing weights, batch normalization, so-called regularization, optimizations, grid search, 5 parameters. Like that, people learn many things, and now they carried these concepts forward by learning from this. Now let's look at object detection. Now, what we have learned up to now, if you present a cat to a convolutional neural network like AlexNet, it will generate a signature, a vector like 4096, for example, and then you have a fully connected network. This is actually the feature generation part. This is actually the classification part, but actually we train both of these, and then you get a vector of 1000 by 1000 because there are 1000 classes, cat, dog, and so many classes, and then you give a probability as the output. So maximum probability is cat, so we name this as cat. That's what we do in the image classification. But in there are the other vision tasks other than the image classification. Now this is the classification. You give one label to an image, no spatial extent. Then there's another slightly difficult problem called semantic segmentation. In the semantic segmentation, we identify the cat area, right? We identify the grass area. We identify the tree area. So every pixel gets a label, right? Sky. Then there's one more slightly difficult problem called object detection. There we want to draw a bounding box around these objects. What is the box that has that object, like dog and another dog and a cat and so on, object detection. And then another difficult problem is instance segmentation. There you can see, like here, you have identified by every single pixel. So this is the dog area corresponding to the dog. This is the area corresponding to the second dog. Not just dog area, but area corresponding to second dog. So if all the instances of dogs have been separately identified as the cat. Okay. So for these things, people came up with this so-called RCNN, region proposal CNN. So what they did was they took an image like that, and they used a so-called region proposal network to say, okay, this can contain an object, this can contain an object, and so on. So those are called region proposals. So after region proposals, they ran a convolutional neural network like we have seen before, and then a classifier and the bounding box regressor. You see, in the previous one, we had this so-called bounding boxes. So these are called bounding boxes. That means in what box is this image? Is this dot? So a bounding box regressor for each of those. So this is called RCNN. Then after that, they came up with the fast RCNN, and I will not describe this in detail. And then they come up with faster RCNN. There are this discovery of these boxes, so-called region proposals, was also done based on the convolutional neural network. Okay, these are called two-stage detectors because they had to have the proposal and then the classification, proposal and the classification. So single-shot detectors, they do it at once. So maybe you have heard of this very famous YOLO. YOLO detector is a single-shot detector. So you run a CNN on the image, and then you divide that into that many cells. And for each of those cells, you locate these so-called anchor boxes, and then that many anchor categories. So these are the number of classes like cat, dog, and so on. And then you do the classification and bounding box regression at those anchor boxes. So yeah. So this is a description about so many of the object detectors that there are. So these are single shot detectors. So you can see the sort of the backbone that they use is the VGG backbone or ResNet backbone or so-called MobileNet and other Inception and so on. But this is also like CPR 2017, like 2017 description, overall mean average precision, how precise is the object detection. So you can see it has not reached that much. So fast RCN is over here. And then you can see fast RCN, if you take it a circle, circle I'm sorry about that. So they are using the fast RCN working if it is a circle. So these are different things that they are showing. So this circle fast RCN with ResNet and so on. So that's because it is green. So that's things like that. Okay. So usually the two-stage methods are faster, single-stage methods are faster, two-stage methods are better in accuracy. These are faster. Sorry about that. Bigger backbones improve performance but are slower. Diminishing returns of slower methods. Yeah, like that. So but after that also things happen. So some of them I captured, but I cannot do it. But I got from this once again from object detection on the COCO test dev. So COCO is a data set. And then you can see the link I have put here. So you can see Dino is the very famous one. Multi-scale swim transform end-to-end query denoising. I don't even know what these things are. Dino. I have not read the paper. I should read it though. Yeah, code is available. So average precision is 63.3 and so on. Mean average precision, you had to add all this. Yeah. Okay. Then there has been another, this is the best paper award, famous paper called Mask RCNN. That's an instant segmentation paper. So you can see, as I showed you before, different people have been given different colors. That means different labels. So instance wise, they have been recognized. That's also based on fast RCNN. Yeah. Then there is another piece of work called Kinetic Segmentation. This is very important for self-driving and so on. If you take the image, this is, you can see instance segmentation. If you think semantic segmentation, you have the sky, the road, and so on, but all cars are in blue. All cars are in blue. But if you take panoptic segmentation, the combination of these two ideas. So each car is defined by a different label, and the background classes are also there. So, so panoptic segmentation is very important for self-driving. There's another paper by a group on panoptic segmentation in 2020, I think, 21. 21, although I was not a part of that paper, I was with that group. So some other beautiful ideas, like there have been image synthesis ideas. So these are done using so-called GANs, generative adversarial networks. Generative adversarial networks, GANs. So you can see here in this famous paper called Pix to Pix, what they do is they give an image like that. So maybe you hand draw it and you generate the actual looking image. You take a satellite image, you generate the sort of map. and you give an image of the facade, you generate an actual facade. You give a black and white image, you generate a color image. You give a hand sketch, you generate the actual handbag. So that things like that. And this is large scale GAN training for high fidelity natural image synthesis. So you can see these all synthesized images are beautiful, right? Beautiful. And this is the 2019 ICC Best Paper Award. They were able to generate images with a single generated. So you can see this is the original image, and you can see they have generated very beautiful different varieties, variations of that. So these birds flying, you can see if you take this one, so many other birds are there, right? I mean, but it's nice that generated. I do not remember about this work, so I should, but I will not talk about it. Yeah. Okay. Then the attention and transformers is the newest concepts that are there in the community. So many transformer papers in the recent 2022 conference. I am also a reviewer of that conference. These transformers, they work with this so-called attention. So you can see now, if we want to detect this dog, so these are the regions that it should attend to. These are the regions that it should attend to. So the network sort of discovers that you should attend to those. So they do it by dividing this image into patches and take these patches, and actually you take this patch and see how similar it is to this one, sort of. That's the idea of attention. So each of the patches, how similar it is to the other ones. So that information is sufficient when you have it in a so-called transformer to actually improve these vision tasks. So the very first paper that came up with this transformers is this very famous Vaswani paper, Attention is All You Need. Then you know all the text generations, searches, and so on in these famous companies by transformers, like BERT is one of them, and maybe you have heard of GPT also. GPT is also one of them. Google's and Facebook's, they have these. And then these techniques are adapted by Dostoevsky to computer vision in this 2021 paper, very quite recent work, right? It's called the VIT, or the vision transform. So these images are from that vision transform. Things improve due to that. Okay. So now before moving forward, we will take a brief break. So you can ask if you have any question, or if you need to know anything, you can ask. Otherwise, I will after that I will show you a few more things about this, and maybe do a little bit of coding and be done with this. You can type in the chat or whatever, so I can answer if you have any question. Anyway, you can take a break also. Maybe we'll start at 7:05. So anything you can ask, type in the chat, you can ask about anything that I can answer. So anything about general things also I can answer. General things about science, so what we do at Moratuwa and so on. Are we generating more than one image in convolution? Are we generating more than one image in convolution? The thing is this, like when you have an image and you do the convolution, you have that many filters. You run one filter, run another filter, run another filter, like that. So you are generating so many image-like things in the convolution. I don't know why this background came. I don't like background. I'll remove that. I don't know why it came. Yeah, when I check, I think I made a mistake here. Yeah, sorry about that background. So that's a good question. So yes, that is correct. What is the best way to start learning the subject? If you're starting out a step wise, yeah, yes. So the answer to that question is, I think it must be hands-on. Otherwise, there is no use. Okay, in any subject, it must be hands-on. Then only you become familiar with that, and then only you can produce something out of that. So I think from our childhood in Sri Lanka, unfortunately, we have been taught in a very different manner than that. Like we have learned to memorize things, right? For maybe for grade 5, you memorize things. For O levels, you memorize things. And if you say exactly the same thing that you have been asked to memorize, you get good grades. But if you ask me, what's the main difference between A levels and the university education, I would answer like that. Now, in A levels, the goal was passing A levels, right? So you are very thankful to the teacher who would train you to pass A levels. But in the university, passing exams is not the goal. Being able to do something is the goal, right? Being able to apply your engineering knowledge to solve problems is the goal. So because of that, the way to start learning computer vision or any other subject is to be hands-on. If you do circuits, do soldering and get the circuits working. If you do computer vision, get the computer vision work done by yourselves. So for that, you have to learn a little bit of Python, as I told you. So the first step is to learn a bit of Python. So you can type for some Python tutorial. I think the Stanford Python tutorial is very nice. So maybe I'll show you that. So this, if you type like Python, NumPy, Stanford, that is the tutorial. So you have to do it. Like you can do it in 2 hours. You can do this in 2 hours, but that does not mean make you a Python man. So you have to do a little bit more. Maybe do a book or maybe do more exercises to learn Python. Then after Python, you have to learn Opencv. That gives you the basics of computer vision. Go to Opencv and then start learning Opencv. Yeah, I'll show you how to get that done. And then afterwards, you have to either take a course or read a book or attend a class like class taught by me. To reach this, the highest level that we are discussing of being able to publish at this level, so you have to do some more courses. So at our university, there are actually 3 levels of courses. The basic course that we do, the image processing and computer vision course, the machine vision course, the finally advanced course, and an extremely advanced course called Advances in Vision. That's a paper reading course. We get together and read papers. That's why the students are able to be taken up to that level. But if you are very keen, I'll be most willing to bring you also into into those groups and make you aware of those things. And yeah, but you have to work hard. You have to work hard. So that's the lineup. In summary, do some Python, do the work on Opencv. I will show you these things today, and then maybe read a book. So I showed you a list of books today, or maybe take a class. So if you look at the Richard Serisky's book, Professor Richard Selesky's book. There he has listed some courses that uses his book, some courses that, so I try to click them today. So maybe you can go inside and see which course has videos, which course has videos, and then maybe learn it. So I know that some courses have videos, like for example, maybe her course, good looking professor, her course her course has let's see whether it has own data teaching I don't know, she's done teaching. Find a course which has videos. I don't know whether she has videos. Slides. Yeah, she doesn't have the videos, but at least I learned much from this person, Professor Justin Johnson, much younger than I am though. If you do not know something, you do not know something, right? So you learn. So maybe the computer vision course has videos. You usually go to the schedule and no, it doesn't have. So find a course that has videos. Maybe you can do a course or something. Any course by a person would be good. So, but Professor Justin Johnson has videos for the this one, learning for vision course, deep learning for vision course. Maybe you can watch those videos. They are actually hard. Honestly, these are hard. So you'll have to watch each video many times and try to understand. Where are the videos? Yeah, YouTube. You see, yeah, he has made them available on the YouTube. That many lectures. Very good. Very good. So you can see the slides. Some of the slides I have used.
I think we should explore a few solutions.
Grammarly suggestions catch me.
Community has
welcome back to lecture 16.
So you can
troops, but is pretty far from being perfect.
Talking about
and we also got this region proposal
object detection and so on.
Transform target. And the story normally think about doing this sampling is that you just want
to. You have to spend time though. Yes. Then sir is the signature of the image taken from the convolution generator. Is a signature of the image taken from the convolution generator. Yes, I think the question is how to convert an image to a signature, right? Yes. So we actually, in the computation language, you call it an embedding. Yes, it is through convolution. So when you convolve, the number of numbers in the image reduces. And then maybe you'll have a set of numbers like maybe 512 numbers that you run with a classifier. So these classifiers can be support vector machines or some neural network layers themselves. So I did not describe this slide, but if you look at one of these slides, this one, you can see they take the image, convolve. Finally, you have numbers, like how many numbers you have here, 16 times 5 times 5. That means you have 25 times 16, 400 numbers. 400 numbers. That's a signature. 400 numbers. That's a signature. Those 400 numbers you connect with 120 nodes, 84 nodes, 10 nodes. This part is a classifier. This is the signature generator for the encoder. We can call it an encoder. So similarly, if you take this AlexNet, that also does this, right? So it has 9,216 numbers, and so on. So this is how these things work. Yeah, thank you for those questions. Okay, so we can start now, I think. This one, I will show you a little bit about computational environments also. Computational environment is expensive. So there are several ways to do that. You can use a GPU machine with cards, like for example, NVIDIA RTX 3090 cards. These cards are expensive, right? Very expensive cards. These are gaming cards. They're very expensive, but they are advanced cards also. I showed you these advanced cards like A100. These are extremely advanced cards. And then otherwise you can purchase computation power from the cloud, Amazon, AWS, Google Cloud Platform, or Google Colab is free. So, but you cannot do too much processing, as you would understand. So here, using this famous, like very nice website called Lambda Labs, it shows these rankings of the GPUs. Right? So the most advanced GPU, or the graphics processing unit, these are video cards. Okay, is this famous A100 by NVIDIA, and once again A100, this NVIDIA, this is a connector, not PCIe, and then A100s, then RTX A6000s, RTX 3090s, and so on. So this V100 was I have a machine with 2 of these cards, and another 2 machines is 2 of these cards. So that's how we do the computation. Well, these cards are very expensive. One reason is they are expensive, and then people use them for computer vision and deep learning, and also people use them for Bitcoin computing, right? All these things they use crypto computing. Yeah. Yes, that's the thing. So then now let's see, like, what are the within computer vision, what are the interesting fields? The way to do that is to look at the CVPR 2021, this one. 2021 distribution of topics. You can see CVPR oral, that means you can present it at the CVPR conference. So our first paper was an oral paper. That's the most, one of the highest categories, highest category. 3D computer vision. So generating 3D things, the very first video that I showed you, that, when you rotate around the table, that 3D thing, that one, and 159 posters. So you can see this category receives a lot of interest. Representation learning and deep learning, image video synthesis. So we show some synthesis videos also, like generating these faces. Those are video synthesis papers. Computational photography. When you make photographs in the computation photography and so on. That means you take high dynamic range images. Maybe you have heard of them. Sometimes your phones can do that. It makes several shots at different exposure levels and then combines them to produce a beautiful image. Then scene analysis and understanding. Yeah, so we looked at many examples of that. Biometrics, face, gesture, body pose recognition, vision applications and systems, vision for robotics and autonomous vehicles, explainable AI, fairness, accountability, privacy, transparency, and ethics in vision, image classification. Now attention is reducing, right? Classification is well understood. Now they are reaching 90%, better than human accuracy. Machine learning, architectures, formulations, motion tracking, vision, language, and vision and other modalities. What that means is, like, you are able to write a paragraph about a video, something like that. Action and behavior recognition. We worked on this area early days, but now we don't work. Efficient training and inference methods for networks, studio object recognition, transfer, slow shot, unsupervised learning, and so on. So I did not talk about those. Vision analysis, understanding medical, biological, cell microscopy, adversarial learning, adversarial attack defense methods, data set and evaluation, 3D object recognition, image video retrieval. That means when you search for images, how do you get them in Google and so on. Optimization and learning methods and so on, right? So many fields. So you have to pick a field that interests you and has some attention in these kind of conferences. Yeah. So before going for the coding part, I'll just summarize what I said. So why computer vision is now, I explained. Why the 2 reasons, why now the hardware became available. Also the industry uses computer vision for work, like face recognition, detecting what people are doing in a store, fingerprint recognition, face login, and so on, right? And then we looked at conventional techniques and the perceptron and the convolutions. And we looked at the convolutional neural networks and the convolution pooling, convolution pooling, and some dense layers and the classification. And we look at image classification methods like AlexNet, VGGNet, ResNets, and so on. Then we looked at object detection methods like RCNN, faster, RCNN, faster, RCNN, and other new methods. And then we briefly look at the transformers, and those are the future trends. So this is these are my contact details. You are most welcome to contact me at any time. So my students have my phone number also, but do not call. It's very difficult to answer many phone calls because I have now a clerical job also. Yeah, yes. So that's what I wanted to cover using the slides. So now let's briefly do a very brief demonstration. I think you also can do that if you like right now. It's not hard actually. Yeah. Okay. So for that, what you need for what I am going to do is to have access to this. You have to have Google account. Google account. So we will do this in Google Cloud platform, not Google, Google Colab. So what you need to do is you type Colab. So maybe you can start doing that now, if you like. You type Colab. So collaborate. It's called Collaboratory Colab. So maybe you can do that now if you're near a computer. Type Colab, and then you'll be taken to the Colab. You click this, and you go to the Colab, and then you can cancel this, and you can say file new notebook. So these are called notebooks. These are called Jupyter Notebooks. So we type this in Python, but it's very easy. You'll see very easy. So you have some. So maybe you can type a title for this code. We will write like KDU. ERIC, I think that's the name of the pub and 2020, whatever the way you would write, right? This is how I do it. 315 and last, something like that. Yeah. Okay. So now my notebook is ready. Yeah. So are we ready to start? So if you have a problem, please let me know. Are we ready? Okay. So let's first look at some easy computation code. People in my class have already done this. For this, we should be able to access the Google Drive, right? Because this is not on the computer; it's on the Google thing. So therefore, our drive, Google Drive, must be accessible, right? So for that, I will first of all do this, right? From Google.colab import drive. So these codes you memorize, right? Memorize and do it. So I mean, this is not something that you can understand, right? You have to memorize. So then you say drive mount so content drive. So you mount the drive so that you have access to that so-called Google Drive in this code. So they will ask you a couple of authorization questions. I have authorized. It will not ask me questions, but in your case, it will ask you whether you should give access to this. So why did you put IPython NV at the book? And maybe you don't need it, but I just put it. Connect Google Drive. Yeah. I think it is asking permissions again. Yes, it is asking me permissions. Yeah, I will say allow. Now it's allowed, and it will run the thing and run it. Yeah, it's connected. So if I hit this button, so I will be able to see my drive and the things that are on my drive. So in this my drive, that's the folder it is mounting. And in this thing called image, I have this beautiful image. Okay. So yeah, now that part is done. So what it is, you add one more coding cell, click code and add that cell. Now I'm going to use Opencv now. Opencv. So you say import CV2 as CV. So this is how you import Opencv. Then maybe you can print the version of that CV. Print the version of this Opencv. You do that by writing version cv.print underscore version underscore. So that will print you the Opencv's version, if you like. So 4.1.2 is it's a very new version. That's there on the Google Colab. So I don't need that anyways. So now I know that the Opencv has been loaded. Yes. Okay. So you are most welcome to do it with me. And then to plot these images and show them, I need another package. So I need this package called import matplotlib.pyplot as plt. So these are things that you have to memorize, and nothing to learn here. Okay, then I'm going to open my image. Open my image. So open the image. So say im. Let's say for that im equals cv dot. Of course, you can see. I mean, it's very easy to understand, right? Im read. So I have now given the path to this. So I said like it's in content drive. So we have to type that content drive, and there it's in the content drive. It's in my drive images, right? My drive and images. So you can put it to the where you like. So I have put it in images, mr.jpg. Yeah. Okay. So after doing that, something that you can do is assert im is not none, just to see whether that image has been opened. Otherwise, sometimes a lot of errors come and you don't know what it is. Then to run that, you click this button. Okay. I said not in where is it? In E, not in is. It ran, so it's fine. So that means the image has been opened. So now I can do things with that image. So the thing that I'm going to do with that image is I'm going to blur it. So before that, there is some cumbersome operation that I have to do. Im equals cv.cvt color. My students in class know what this is, but please do that. im.cv.color bgr to RGB. BGR to RGB. Let's see whether that works. Yeah, see how it will color BGR to RGB. So I'm using this as a spell corrector. Google will not be happy. Yeah. Then let's blur that image. Blurred image equals CV dot. I mean, blur functions and so on. So many of them are there, but I will use Gaussian blur. Gaussian blur. Okay. But before that, shall I do that using Gimp? Okay, to do that in Gimp, you try Gimp. So some of you have Photoshop. So since I have only the good software on this machine, I have only free version. This Gimp is a beautiful free package for image manipulation. GNU image manipulation platform. So yeah, opens that. So these things that we do on this one, we can do using Opencv. Let's open an image file. Let's open the image of so many folders, so many. Let's open an image from these people's. Yeah, so open the image of. Open the image of. Yeah. Yeah. Not good. Don't like that. Yeah. Good. No, I don't like that. Too small. Let's see. Open the image of. This one. Image of Hugh Jackman. Wolverine, right? What an actor, what an actor. Right? You see the expressions that he gives. Hugh Jackman. Oh my goodness. So to do Gaussian blur, you do filter, blur, Gaussian blur. See, filter, blur, Gaussian blur. It's blurred, right? This is what we are going to do. Filter, blur, Gaussian blur. Okay, so now let's now do something like, let's take that you took a stupid image like all focus image. You should take an all focus portrait. All focus portrait image. Let's take some all focus portrait image. I hope we will not see add images. I want to show you how this is done in Photoshop also. Like I don't want to do Photoshop now, but I will show it, right? I will take an all focus image and show you how you can make an image look beautiful. I don't see that kind of image. These all the portrait images have been not properly taken. It's incorrect. Incorrect portrait images. I should have prepared for this, right? Portrait image with background. In focus. I want to show you how to make a stunning image. This one is good, right? Okay, let's take this. What I want to do now is to show you what these things can do. How you process images. Like, some of you maybe, some of you are people who process these images. Okay, see now, what I want to do is I want to select this person. So make a selection. So click this, and these areas are selected. Maybe let's select using the color. Select by color, not selecting properly. So that also doesn't work. So maybe what you can do is select manually. So select using an ellipse. Select none, and take and draw an ellipse to select this person's face. So maybe I'll do a bad job there, that's okay. And then add to the selection and draw more ellipses. Oh, click the wrong one. So draw this like that. In Photoshop also you can do this same thing. Huh? Photoshop. Draw another ellipse to select that part. Draw another ellipse. So like that you draw these ellipses and select this person properly. Okay, let's assume that this person has been nicely selected. Okay. Now what you do is say select, maybe let's shrink the selection a little, maybe by like 10 pixels. Shrink the selection. This is not good. I will add one more selection part here. Okay, now it's okay. Now let's say like maybe grow it a little, then it will smoothen out. Grow the selection, and then you say select and feather. Do some feathering, and then you say select invert. Invert the other one, and then you apply filter, blur, Gaussian blur. So you blur it, and you see you blur the background, right? So image looks extremely beautiful. If you properly selected, that image will look like a nice portrait one. So unfortunately, we did not properly select. So these are things that we can do with that. So that's what we can do. But selection and so on, I did not do. That's what Gaussian blur means. So for the Gaussian blur, we have to have an image, and like the numbers that I input in the Gimp, I have to give like maybe 11 by 11, and then maybe another number. So about these numbers you will learn later on in the classes. Then I had to show this. So I had to create the figure axis. I would say plt.subplots, and then say IM subplots, and then how many, size of the plot that I want, number of plots that I want. So I want 1 and 1 by 2, and figure size, maybe I want 10, 20. Yeah, that's also okay. So in the first axis, AX0, I want to show the original image IM. Then I want to do a little bit of things to get rid of the axis, things like 0.axis off, something like that. So that's the image, and then the second image is the blurred image that I want to show, this blurred one. Blurred, and then this is one in the first axis. Then I have to say PLT show. Okay, the code is done, you run it. Yeah, you can see this one is blurred, right? The second one is blurred compared to the first one. Yeah, that's very simple code, you can see. So you can have fun with these things. Do a little bit of things and have fun. Maybe you can create your Facebook profile image using this. Okay, let me not write the reason for that. Yeah. It's very easy, right? This part we don't need. So that's the first piece of code. Very simple. So now you can see, like, here I did the blurring, so you can do a multitude of operations there and get the effect that you want. This is called image processing. So maybe we'll do a little bit more aggressive blurring. Aggressive blurred, right? Yeah, I hope it is okay. Then next one we are going to do is some edge detection. So I will quickly show that to you. So the first part of the code I will copy and paste, and then second part of the code also I will copy and paste. But now I'm going to do edge detection. So edges equals cv.canning. That's the edge detector in Opencv. So I give the image and two numbers. I will not explain how those two numbers come, but just to show you this. Yeah, edges. Yeah. Yeah, you can see the original image and the edges of that. Okay. Yeah, that's the edge detection. So like that, you can do a lot of things. So these functions are available in Opencv. you have to go to the Opencv documentation and understand them one by one. So a lot of tutorials are also there. So you can learn from those tutorials. Okay, if you have any questions, I can answer. Otherwise, I will move to the last example, a small code of text detection. So for that, we will use a TensorFlow. I hope you are ready. Import TensorFlow. This famous deep learning library of Google. Then we need from TensorFlow import Keras. So these things don't ask me why, so you'll understand why later when you do that. And then of course matplotlib. These for plotting. So then let's print the TensorFlow version. Print tf dot underscore underscore version underscore underscore under. So TensorFlow 2.8, it's a new version. Okay, and now we'll have to open the data set. So it's called NNIST, the digit data sets. That's a very famous data set by Professor Jan LeCun. So we show his network LeNet also. Keras dot datasets dot NNIST. Yeah. And so now we import that data set. So it's very easy for us to get these things done in Colab. And then, so you have to divide that into the training and testing set. Training and testing set. So I'll do that part now. So X train, Y train, X test, Y test. Yeah. Equals MNIST load data. Okay, so you load the data set here. Then we can you can display those images. Let's do the displaying code. May I copy that part of the this clt.figure size. So these are parts of code that you have to remember. I mean, you cannot memorize. I mean, take from some place, you cannot memorize this. So I also have copied them. So for writing a for loop, I in range 25, I'm going to print 5 by 5 images. plt.subplot 5, 5, I plus 1. Yeah. In that particular subplot plotting. So don't worry about this code, it's not part of the processing. So reshape the particular image, extrain ith image. 32 by 32. Yeah. And then I need, okay, let's 28 by 20. I think these are 28 by 20. Let's see whether it works. Spelling mistake. you can see these are the numbers. So some of the numbers, I think there are 50,000 numbers here. Some of the numbers I displayed for us to know what it is. And now there is a little thing that I have to do, that is to data type change. So x train equals tf.data type d types dot cast. So train data type. So you'll understand about this when you actually learn these things. tf.float32. I hope that is correct. And we have to do this for the test set also. For the X test. So training set and testing set. X test. That's okay. And then turn the size of them, x train comma x, not the type, shape of them equals x train. Don't ask me what these things are. If you have to do a little bit of Python and NumPy to understand. Divide by 255. So then it trains better. So we did not actually still type the code related to neural networks. We are still preparing things. So therefore, you cannot say, okay, this is taking time. This is just preparing. So that part is all okay. Now actually we are going to type the model. Model is a neural network. Model equals. So keras dot sequential. Keras dot layers dot flatten. So flatten the thing that actually this is what we are doing is not a new convolutional neural network, but just a neural network, dense network actually. So that layer is fine. And then the next one is keras dot layers dot dense 200 activation. So ReLU. So we looked at these activations earlier. ReLU. That's okay. And then we that's okay. Keras. Layers. Okay. Yeah. Yes, it's okay. So the last one. Last one is it must be equal to the number of classes. So it's actually 10 classes, 10 digits. Keras dot layers dot dense, number of classes 10. Okay, and then I have to close this bracket. So that then our model is done. Then I had to say model dot compile, and then I have to give an optimizer. We briefly talked about optimizers. Optimizers, this famous optimizer called Adam optimizer, and then what is the loss? We talked about the loss at the very beginning. tf.keras dot losses sparse categorical cross entropy. Yeah, so these are some from logics. True. So what is the difference between computer vision algorithms, machine learning algorithms versus AI algorithms? So I showed you the very first slide. So AI is the large area where AI just tries to make the machine behave like human beings. So maybe some parts cannot be coded in algorithms. So machine learning is getting the machine to learn. So computer vision is getting the machine to learn to do computer vision tasks. So in computer vision tasks, there can be machine learning based tasks and the conventional computer vision tasks. So here there was no learning, right? So that is also actually it's image processing. So I mean, we don't call it machine learning. So here we are applying deep learning part in this one. So I hope I answered the question. So so logits.true, and then I have to give the metrics. Metric equals accuracy. So I showed you some accuracy results from the very recent course, right? You can say print model.summary. It's always good to print the model summary. So let's see how many layers and so on are there. Run the code now to see if there are any errors. Maybe there are errors. Okay, so you can assign layers. So spell checking. Model layers has been shattered. Using Colab as a spell checker, Google will not be happy. Oh no, what is it saying? Let me see. Model.compile, optimizer, Adam, that's correct. Loss equals TF, Keras, losses, sparse, categorical constantly from logits true, that's also correct. Matrix accuracy, looks okay. What is it saying? I'm missing a parenthesis or something. Optimizer, Adam, loss equals TF, Keras, losses. Sparse category constantly from logits true. Metric, matrix accuracy. Yeah, so you can see that this is the first flattening and then a dense layer and then another dense layer. So number of parameters and so on are displayed. Now we have compiled a model. Now we have to run it. So we say model.fit. So in machine learning literature, this we compile the model and then we run it. You train it with train it. That's called fitting. X train dot py train. So how many times we present the data set again and again? Like let's do it 10 times. Epochs equals 10. And then after that, we have to like test loss. Test loss equals okay, test loss comma test accuracy equals model dot evaluate. Model dot evaluate is with the test set x test, y test, verbose 2. Yeah, it's okay. And print test accuracy. Test accuracy. Yeah, so it will take some time to train. So before training is bad idea. Okay, here 28 and 28. Yeah, you can see it's training accuracy is already at 80%, right? 92%, 93%. So 10 times it will run epochs 10. So many epochs are usually run, like sometimes hundreds and thousands, 300,000 sometimes for these things, for some different things. 94% accuracy on the training set, okay, not on the test set. Test accuracy will be less, 95%. Yeah, with this very simple small network, right? Yeah. 9th epoch, 10th epoch, done, and you sit there. Oh my goodness! Oh, test accuracy is 0.0 now. Something is wrong. Did I not do something with the test set? I know. Yeah. I did not cast, right? Yes, also done. X test 255 division is done. Oh, this is the problem. Trained on the wrong set and tested on the wrong. Is a tree, right? That's the problem. Run that again. Training accuracy is high, testing accuracy is low because the data sets are different, because that's the problem. Yeah, now it's 97%. Even, yeah, it's good. Okay, so that's all I wanted to cover for today. So if you have any questions, you can ask. Otherwise, we can be done. Please ask if you have any questions. So very simple code of digit recognition, right? Recognizing these digits. So they have been properly recognized. Handwritten digits. Yeah. If you have questions, please ask. Otherwise, we can be done for tonight. So what we did was we studied about image processing, computer vision, and novel trends, and we did some little bit of coding also. So I encourage you to do it by yourselves and start learning, and you'll feel very happy about it. I wish you all the very best for your future in computer vision.
Guys, if you have any questions, you can clarify them right now.
Is there a diploma program that we can do in Sri Lanka? You can do the BIT if you like, but if you're doing a degree program there, you don't need a diploma from Moratuwa. Yes, Sorry about that. Sorry, I asked the question. Please go ahead.
I hope there's no questions anymore. On behalf of the Electronic Robotics and Innovation Club of KDU, I would like to express my deepest appreciation to our guest speaker, Dr. Ranga Rodrigo, for conducting such an informative session. Thank you so much, sir, for all that you have brought to the table. Dear sir, please accept this digital token of appreciation.
Well, thank you very much.
Thank you, sir. We are almost at the end of the event, so I would kindly invite you all to switch on the cameras to capture a moment of the event. I once again request you all to switch on the cameras to take a picture.
Oh, the Dean sir is also here, so welcome, sir.
Under my countdown, say cheese. 1, 2, 3. Thank you, everyone. Before we wrap up, I cordially invite Yehan Kodituapu, the Secretary of ERIC KDU, to deliver the vote of thanks.
Thank you, Brittany. Our guest speaker, ladies and gentlemen, on behalf of Electronic Robotics and Innovation Club of General Sir John Kotelawala Defense University, and on my behalf, I would like to extend my hearty gratitude to the guest speaker of today's event, Dr. Ranga Rodrigo, for gracing this event. Thank you, sir, for dedicating your time on the computer vision organized by ERIC KDU amidst the busy schedule. We believe that the knowledge you shared throughout the session resulted in a positive outcome on the audience, and we are grateful for the guidance you gave on learning the new scope. I owe special gratitude to our mentors for the guidance and encouragement given to us. A big thanks goes to all the participants from all the faculties of engineering and computing who witnessed the session. Also, my appreciation goes to the team members of ERIC KDU who worked towards the success of the computer vision workshop. Next, I extend my thanks to all who did support us in none other ways. If it wasn't for you, this would have been a reality. Thank you so much.
Thank you, Yehan.
Thank you, Yehan.
And that marks the end of today's event of Electronic Robotics and Innovation Club of General Sir John Kotelawala Defense University. I'm Brittany Sintuja, signing off for the evening. Thank you and have a good night, everyone.